The tangent and velocity problems. Here we look at the problem of finding the equation of a tangent line. So first we need to understand what is a tangent line. So let's recall from geometry that we learned that a tangent line to a circle is a line that intersects the circle in a single point. So we can think of this as the line grazes the circle. For a function, it's the same concept. So we can see at point P here on the graph of this function, the line barely touches the function at that point. Now it also hits the function over here, but that doesn't change the fact that at point P, we have a tangent line. Let's take a look at an example. Here we want to find the equation of the tangent line to the parabola y equals x squared at the point P, which has coordinates 1, 1. So you can see we have the graph of our function y equals x squared, and we have the point P shown on the graph. So the tangent line is going to be the line that barely touches the function at this point. And so we know that this line is going to look something like this. To find the equation of a line, you need to remember that we need to know two things. We need the slope of the line, and we need a point on the line. Well, we have the point on the line because, again, we know that this occurs at the point 1, 1. The problem is we need to find the slope of this tangent line. So this is really the focus of this section. So let's recall that if I have a point on the graph of y equals x squared, and our point is 1, 1, and if I pick some other arbitrary point on the graph, say this point up here, which has an x-coordinate x and a y-coordinate y, let's recall that we can rewrite that point xy as the point x squared. And this is because this point is on the graph of y equals x squared. So x squared can substitute for y. So let's go ahead and rename this point x squared. Now let's talk about finding the slope of this line. Now this is not the tangent line. This is what we call a secant line, as this line intersects the graph in 2 points. So let's recall how we find the slope of a line. We can do this by remembering that the slope of a line is found by subtracting the y-coordinates of the points divided by subtracting the x-coordinates of the points. And for this particular line, the y-coordinates are x squared and 1. So we can say x squared minus 1 divided by the x-coordinate is x and 1. So divided by x minus 1. And now for any given x value, I can find the slope of that line. So for example, if x is equal to 3, the slope of the line that goes through the point 1, 1 and the point up here corresponding to x equals 3 is going to be 3 squared minus 1 divided by 3 minus 1. And if you simplify this, you get 8 divided by 2, which is 4. Okay, and I did that by simply taking x equals 3 and plugging it into this formula for the slope. And I can do this for any x value. So for example, if x is equal to 2, the slope of the line would be 2 squared minus 1 divided by 2 minus 1. And this simplifies to 3 divided by 1, which is 3. And this would be the slope of the line that corresponds to x equals 2, which is this point on the graph, and then we could graph that line, which would go through those 2 points. And again, we can do this for any x value. So here are both of those lines graphed. So we have the secant line corresponding to x equals 3, and the secant line corresponding to x equals 2. But let's keep in mind that we are trying to find the equation of this tangent line. So we need to know what is the slope of this tangent line. So what we need to recognize is that if we pick a value of x that is closer to 1, the secant line begins to look more and more like this tangent line. So how do we find the slope of any secant line? Let's remember that it's x squared minus 1 divided by x minus 1. And we can let x be equal to any number as close as we want to get to x equals 1. So let's suppose we let x equal 1.1. The slope of the secant line would be 1.1 squared minus 1 divided by 1.1 minus 1. And this is 1.21 minus 1 divided by 0.1. And this is 0.21 divided by 0.1, which simplifies to 2.1. Now, that line would be really hard to graph here because 1.1 is right about here. And if we put that point on the curve, you would see that the secant line here is very, very close to this tangent line. So what we should observe is that the closer this number x gets to 1, the more this slope is going to be close to the slope of the tangent line. So one final example here. Let's suppose I let x equal 1.01. The slope of the secant line would be 1.01 squared minus 1 divided by 1.01 minus 1. And if you do the math on this, you get 2.01. So I want you to see that as x moves closer and closer to 1, the value of the slope appears to be getting closer to 2, right? Because we had 2.1 and now we have 2.01. And this is the basic process for finding the slope of a tangent line. So I'd like to introduce a little bit of notation to you. If I'm looking for the slope of the tangent line, this is going to be equal to what we call the limit as x approaches 1 of x squared minus 1 over x minus 1. And this is basically saying that the slope of the tangent line is equal to the slope of the secant line as x gets closer and closer to the point of tangency. And we're going to spend the next few lessons talking about how we can compute this limit. For right now, the way we compute this limit is we just pick values of x that are getting closer and closer to 1, like we did on the previous page. But I should also mention that I could let x be equal to a number on the other side of 1, right? Because I only picked values on the right side of 1, but we could have chosen values on the left side of 1. So for example, if I let x equal 0.99, that's a number that's really close to 1 on the left-hand side. The slope here would be 0.99 squared minus 1 divided by 0.99 minus 1. And if you do the math on this, you get 1.99. So you can see that when we pick a number that's really close to 1 on the other side, we are still getting a slope that is really close to the number 2. So it seems like the slope of the tangent line is equal to 2, because that appears to be the number that we are getting closer to each time we plug in a value of x that is close to 1. Now let's remember at the beginning they asked us to find the equation of the tangent line. So once we figure out that the slope of the tangent line is 2, we can find the equation of the tangent line by using the point-slope formula of a line, which is this formula here. And again, we know the point of tangency is the point 1, 1. And now we know the slope of the tangent line is 2. So we're just going to plug in the value 2 here, and then plug in 1 for y1 and 1 for x1. And when we do that, we get y minus 1 is equal to 2 times x minus 1. Multiplying this out, we get 2x minus 2, and finally solving for y by adding 1 to both sides, we end up getting the equation of the tangent line is y equals 2x minus 1. But finding the equation of the tangent line is kind of an afterthought. The hardest part, the part that has the most work, is the slope of the tangent line. For the second example, let's take a look at a velocity problem. If a rock is thrown upward on the planet Mars with a velocity of 10 meters per second, its height in meters t seconds later is given by the equation y equals 10t minus 1.86 times t squared. Now, I went ahead and graphed that function on a graphing calculator so you would have it for your reference. What I'd like to do now is find the average velocity over the given time intervals. So I want to find the average velocity from t equals 1 to t equals 2. So t equals 1 is right here. And on your graph, that is this point right about here. And t equals 2 is right here. And on your graph, that is right about here. Okay? To find the average velocity, you need to find the distance traveled divided by time. So let's remember that velocity is equal to distance divided by time. But the distance traveled, you can see on the graph, is just the distance that you travel from here to here. Okay, so all we're doing is we're taking this y-coordinate, which I will call y2, and this y-coordinate, which I will call y1, and we are subtracting those to find the distance between them. And then down below on the other axis, we have t1 is here, and t2 is there. And the total amount of time between here and here is t2 minus t1. So what I want you to see is that this is the exact same formula as the slope of the line, right? In other words, if I were to graph the line that goes through those 2 points, the slope of this line would be this formula. Next, I want you to notice that in all of these problems here, the first coordinate is always 1. And what they're doing is they're picking values of the second coordinate that are getting closer and closer to 1, right? I mean, you can see in the end here, 1.001 minus 1 is a very small number. So that means that these two numbers are very close together. So the process for finding the average velocity on each of these intervals is identical. So let's go ahead and do a couple of them, and I'll leave the others for you to do as an exercise. So let's find the average velocity on the interval from 1 to 1.1. To do this, let's figure out when t equals 1.1, what does y equal? Well, y is going to be 10 times 1.1 minus 1.86 times 1.1 squared. And if we do the math on this, we get 8.7494. Now, when t equals 1, this y-coordinate is much easier to compute. y is going to be 10 times 1 minus 1.86 times 1 squared. And this is just 10 minus 1.86. And this is 8.14. So now to find the slope of the tangent line, which is the same as the average velocity on this time interval, we are going to take these y values, 8.7494 minus 8.14, right? So we subtract those y values, and then we divide that by subtraction of the t values. And if we do the math on this, we get 6.094, and this will be meters per second because this is an average velocity over that time period. So now let's do the same thing for this part of the problem. Let's find the average velocity on this time interval. So when t equals 1.001, y is going to be 10 times that number minus 1.86 times that number squared. And when you plug this into a calculator, you get a pretty long decimal. You get 8.14627.814. And we already know that when t equals 1, the y value is 8.14. So the slope of our secant line, and therefore the average velocity, is going to be the subtraction of these two numbers divided by the subtraction of the time values. And if you do the math on this, you get 6.27814. And so from this, they want us to estimate the instantaneous velocity when t equals 1. So when t equals 1, the instantaneous velocity would be the same thing as the slope of the tangent line. So how would we estimate the slope of the tangent line? Well, you have to take your previous two estimates and do the best you can. And it's kind of hard to see what these numbers are approaching in this case. But if we just round this to the hundredths place, this number would round to 6.28. And so I'm going to estimate that the slope of the tangent line, and therefore the instantaneous velocity, which means how fast the rock is traveling when t is exactly 1 second, is equal to 6.28. And let's remember that this is given in meters per second. In closing for this section, let's take a look at the graph of that last example. What I want to stress to you is that when you find the slope of a secant line, in the context of velocity, that is an average velocity. And when you find the slope of a tangent line, that is the same as the instantaneous velocity. Or to say that more generally, the slope of a secant line is the average rate of change, and the slope of the tangent line is what we call the instantaneous rate of change. So whatever your function represents, so in the case of the last example, our function represented the height of a rock that was thrown on Mars. So the slope of a secant line is the average rate of change of the distance that rock has traveled, or the height of that rock. And that is why it is the average velocity, because rate of change refers to velocity in this case. The slope of the tangent line represented the instantaneous velocity. At that second, how fast is the rock traveling? So this is something that is important to keep in mind as we move forward. And this concludes this video lesson.